Hello, and welcome. Thanks for having me here. It's a great pleasure to give this week's asymptotic safety seminar from the beautiful Odense in Denmark on light fermions in color. And without further ado, this is my plan. So I'll first give a brief overview as to the larger context of this work, which is chiral symmetry breaking as a test of quantum gravity. Then I'll sort of go through the framework or model and kind of the formalism we use to discuss chiral symmetry breaking. And then I will basically present our main results, which is the fixed point structure of fermions with a color degree of freedom. And finally, I'll give a short summary of our results. So to remind you about chiral symmetry breaking, and here I will be interested mainly in sort of chiral symmetry breaking the way we know from QCD. So you have a condensation of meson of the meson field, and we would like so in that sense, chiral symmetry breaking, not the chiral symmetry breaking through the Higgs mechanism. Now, in QCD, you have a dimensionless gauge coupling, which means that when you the scale at which chiral symmetry breaking sets in has this natural hierarchy with respect to the UV scale at which you initialize your RG flow. This kind of relation goes under the name dimensional transmutation. And so in QCD, if you have sort of just pure QCD and chiral symmetry breaking triggered by gluons, then the QCD scale and the scale of the mesons will be much smaller than the Planck scale. So in that sense, QCD bound states are light. Gravimesons, now you could imagine building mesons held together by gravitons. And this is not an unnatural proposition because gravity is attractive and it is universally attractive. However, there are dissimilarities to the QCD picture. Firstly, gravity is universal, unlike QCD, which has sort of color neutral fermions. So electrons, for instance, do not form mesons due to gluon exchange because they're not charged under the SU3 gauge group. Gravity, on the other hand, is universal. All fermions interact with the metric field. Furthermore, the gauge coupling in the case of gravity has a finite mass dimension, and it becomes strong at the Planck scale. And so there is no such dimensional transmutation mechanism. There is no natural large hierarchy between the Planck scale and the mass of gravimesons. And combined with the universality, it would mean that all fermions would have roughly the Planck mass, which is of course bad because we know that there are light fermions in nature, light compared to the Planck scale. And so the upshot of this discussion is that we should avoid chiral symmetry breaking induced by metric fluctuations if we want to have a phenomenologically viable theory of quantum gravity. And of course, the fact that gravity is universally attractive means that this is not an obvious statement, but it has to be shown by explicit calculation. And the first calculation in this regard was done by Eichhorn and Gies Astrid Eichhorn and Holger Gies in 2011, where they showed that if you only have neutral fermions, so fermions that are not coupled to gauge fields of any kind, apart from gravitons, then metric fluctuation-induced chiral symmetry breaking is avoided, no matter how large the gravitational coupling becomes. If these are charged under a U1 gauge group, an Abelian gauge group, so that's kind of the electric charge, then Gustavo, Mark, and Astrid showed, and I think, let me just check, 2 out of 3 of the authors are in the audience at the moment. Hello. So they showed that you basically can get chiral symmetry breaking induced by metric fluctuations if the number of flavors is too small. And flavors in this sense, because there is no SU2 gauge group, flavors roughly correspond to generations in the language of the standard model. Yeah, and so in this talk, I'll be presenting work I did with 2 of the authors appearing on this slide, Gustavo and Astrid, on extending these considerations to the case where the fermions are further charged under a non-Abelian gauge group, namely SUN, the SUN gauge group. Okay, so our model, we have a model of gravitons, gluons, and photons, and the fermions are minimally coupled to all of them. This is kind of thing that you can do. Note that all fermions have the same electric charge and the same color charge. This is kind of so the color bit is okay, but so there are no color neutral fermions, which the standard model would have. And also in the standard model, different particles have different electric charge. Different fermion particles have different electric charge. None of that is in here. However, we do have basically the gauge structure, or part of the gauge structure, which is U1 cross SU3. Of course, the actual standard model is a lot more complicated, but this is kind of our starting point. Okay, so the fermions have a fundamental color index and a flavor index. And again, because we don't have an SU2 gauge group, you have to think of the flavor more or less as what one would call generation. Okay, and we have the gluons in the adjoint representation. Right. Now, to diagnose chiral symmetry breaking, we do that by checking for divergences of the proper four-fermion vertex. And you can kind of understand that by Hubbard-Stratonovich transformation. So basically, you can understand a four-fermion vertex as kind of a meson exchange process where you can, of course, have many different kinds of fermion bilinears with non-trivial index structures. Now, so from the Hubbard-Stratonovich transformation, and if you assume that you have more or less point-like vertices all around, which we will assume here on in, then this amplitude will be proportional, roughly speaking, to the inverse of the effective potential evaluated at 0 if we are in the symmetric phase. And so if this vertex diverges, then this kind of shows that the curvature of the effective potential of the meson effective potential at the minimum is vanishing, and that is the sign of spontaneous symmetry breaking. it is the onset of meson condensation. And the sufficient condition for a chiral symmetric universality class is that you have a fixed point which is infrared stable in the space of four-fermion couplings. Because if you have an infrared stable for fixed point, then the flow, at least in the vicinity of it, will be attracted to it, and you will not get any divergences in the deep infrared when you flow down to the infrared. If you, on the other hand, in a beta function where there are no infrared stable fixed points, you will flow off to infinity. So you will reach a divergence of the four-fermion vertex within finite RG time, and that will signal the onset of chiral symmetry rating, of the formation of a meson condensate. Okay, and within this kind of language of four-fermion couplings, the work by Astrid and Holger, so Eichhorn and Gies in 2011, they showed that yes, gravitational or metric fluctuations induce a certain fixed point value for certain four-fermion couplings. However, you can actually avoid a collision of the Gaussian or what is left of the Gaussian fixed point, which is called the shifted Gaussian fixed point, with finite valued couplings, which are called in general Nambu-Jonas-Lasinio type fixed points. Incidentally, that work also showed that it is important to have to take into account all symmetry allowed four-fermion channels, because the larger dimensional nature of the theory space allows the different fixed points to avoid each other, essentially speaking. If you have only one, if you only have one coupling, the coupling that is generated, but you do not take into account all couplings that are symmetry allowed in the neutral fermion case, you will have fixed point collisions, simply because you are artificially reducing your theory space. And the case for charged fermions, well, there it was, what happens is the electric if you have in addition an electric coupling, electric gauge coupling, then if they become strong enough, then they can form bound states. So they do also enhance the chiral symmetry breaking tendencies. And the fixed point value for the Abelian gauge coupling, recall that QED has a Landau pole, and if you couple it to asymptotically safe quantum gravity, then you get an interacting UV fixed point for the QED sector, for the Abelian gauge sector. And the fixed point value of the Abelian gauge coupling is proportional to 1 over square root of NF, where NF is the number of generations, so to speak. And so this large fixed point value leads to a conflict with the tendency of the combined metric and Abelian gauge fluctuations to form bound states. So what we and generally such calculations are performed within a framework called functional renormalization group, and this is mainly to fix notation and not a systematic introduction into the functional renormalization group, but essentially you have a kind of a master flow equation of the functional renormalization group, which is kind of one loop exact. However, if you do a fixed point iteration a solution of this with a fixed point iteration and start with the classical action, then what you get is essentially the loop expansion. However, in quantum gravity, what is typically done are self-consistent solutions, and so you take an ansatz for gamma k and solve and truncate both sides of the equation to the space of couplings included in the ansatz for gamma k, and you solve whatever you get self-consistently. And often what one does is expand in canonical dimension and just keep the least relevant terms. The ansatz we chose, which kind of defines our approximation, is pretty much a standard ansatz in gravity matter theories, in computations on gravity plus matter. And that is this kind of ansatz where you first take the classical action and upgrade the couplings to the running versions and account for the wave function normalization. In addition, here you need the gauge fixing. You need to add the gauge fixing Lagrangian, and important in this setting is also the basis of four-fermion couplings, whose flow we need to track in order to keep track of chiral symmetry breaking. And here it is important that we take into account a complete basis, and the complete basis in the setting that we have, where we have in addition to the generation index, we have a color index, the generation/flavor index. So I'll use the term flavor generation sort of synonymously in this particular talk and in this presentation, and also in the calculations, because they behave more or less the same way. Now here you have four independent couplings. Two of them, they're called the V plus A and V minus A channels. So vector and exovector. These have the same symmetry as the kinetic term of the fermions, psi bar d slash psi, and that is the full set of rotations in the NF times NC dimensional space. So if you sort of take all components of direct components of your fermions and pack them into one vector, and then so that's a much larger symmetry, and that is also the four-fermion terms that have the same structure as the kinetic term in terms of symmetries. They are also the ones that are generated by metric fluctuations. So all four-fermion interactions generated by metric fluctuations live within this higher symmetry theory space. The terms with non-trivial internal structure, they are not generated by metric fluctuations. And this will be kind of important soon. And so we come to a result, which is the fixed point structure of fermions coupled to metric and gauge fluctuations. And to set and kind of as a warm-up example, let us switch off all gauge fluctuations. And also we shall treat the gravitational fixed point values as free parameters, because there are large systematic uncertainties in that determination. Now it turns out that for all values of the gravitational fixed point coupling, so for the Newton coupling, there exists an infrared stable fixed point. This is in agreement with what the original light fermions work by Eichhorn and Gies in 2011, what they found. However, it turns out that here the full symmetry of the kinetic term is stable in an RG sense only if the Newton coupling is small enough. Otherwise, what happens is, and so these phase portraits here these are in the space of couplings that do not have as large a symmetry as the kinetic term. You find that for small g, for small Newton coupling, the Gaussian in this space, but of course the symmetric couplings, the higher symmetry for fermion couplings are non-zero at the shifted Gaussian fixed point, but they're Gaussian with respect to the fixed point, the Gaussian with respect to the lower symmetry for fermion couplings. And so this fixed point is infrared stable for small g. And then there's a fixed point collision with a lower symmetry fixed point. And then you get a different fixed point that is infrared stable. And that fixed point no longer has the full symmetry of the kinetic term. And this comes about because you have multiple different channels, interaction channels with different internal structure that are allowed if you have this additional color degree of freedom. So what happens is a fixed point collision without an annihilation, but just an exchange of stability. And especially within statistical physics, this has a fairly long history where the universality class of a certain transition changes as a consequence of fixed point collisions. However, you still have second order phase transitions, but they have a different universality class. Okay, now we switch on the couplings, and so if you recall the concept of dimensional transmutation, the fact that you want to have your chiral symmetry breaking scale to have certain value puts a bound on the non-Abelian gauge coupling at the Planck's or at the UV scale, in this case the Planck scale. And also depending on what your value is for lambda UV and lambda chiral symmetry breaking, you get different bounds. And so, for instance, a natural bound is to say, well, we want to initialize our standard model flow, RG flow, or at least our QCD RG flow at the Planck scale, and we want to have chiral symmetry breaking not happen exactly at the Planck scale. And in this case, you get a kind of bound for the non-Abelian gauge coupling at the Planck scale of roughly 3.3. And it turns out that in the combined gravity gauge system, the fluctuations of the bosons, they all favor chiral symmetry breaking. And so if you increase the Newton coupling, then you get a decrease in the critical value of the non-Abelian gauge coupling. And furthermore, if you increase the Abelian gauge coupling, then you also get a decrease in the critical value of the non-Abelian gauge coupling. And this effect is sharper or more drastic if you have a small, in absolute terms, a small value of the cosmological constant. Okay, now 3.3, is that a sharp bound or not so sharp bound? So the natural point to the natural kind of bound to compare this with is the phenomenological bound that you get if you just want the chiral symmetry rating scale to be roughly 300 mega electron volts. And then you get that the Planck scale value of the non-Abelian gauge coupling should be somewhere between 0 and 1. It kind of depends on details of the calculation, but it should be, it's a much sharper bound. The phenomenological bound is much sharper than this internal consistency kind of bound. However, it's kind of a demonstration of the principle, of the basic principle that wanting to avoid trans-Planckian chiral symmetry breaking, so in the strong gravity, in the regime where metric fluctuations are important and strong, does sharpen the bound then. And of course, so there is a hypothetical scenario that if you want to avoid kind of chiral symmetry breaking in the trans-Planckian regime, then that bound would be way smaller, for instance. So this is kind of a not phenomenologically likely scenario. However, you could see, for instance, here, if you were somewhere in this region where your G critical in the trans-Planckian regime is already way smaller than 0.5, then your lambda QCD would come out to be much smaller than what we observed. However, this seems unlikely if you use realistic fixed point values for the gravitational couplings. However, if you want to do kind of a full calculation, then there are other challenges. For instance, the fact that you would need to make conversions between different RG schemes. So the perturbative QCD calculations, which are kind of the most reliable once the non-Abelian gauge coupling drops below 1, those are performed in a very different scheme compared to the RG schemes that we use in the trans-Planckian regime where gravity is active. Okay, this brings me to my last point, which is more of a metaphysical point than a phenomenological point, which is trading freedom for safety. And I'll only comment on non-Abelian gauge theories rather than life in general. Namely, if you recall the phase diagram of non-Abelian gauge theories, SUNC gauge theories, and at 0 temperature and chemical potential, and furthermore, if you go to the Veneziano limit, where you send both the number of flavors and the number of colors to infinity, but at a fixed ratio, then you have different possible phases. And the kind of beta functions that we were working with, we can distinguish between asymptotically free and asymptotically unfree. But in general, there are some intermediate phases like the infrared conformal or Banks-Sachs regime. And also you have kind of the large NF regime where you can actually get, depending on details of your theory, you can get a kind of UV safe completion. But I'll just mainly focus on the fact that you can lose asymptotic freedom. And the question is, can you then, without possibly relying on subtle cancellations between terms of different loop orders, can you get a UV safe universality class? And the answer is yes. So if you couple to asymptotically safe quantum gravity, then you can complete the non-Abelian QED. So this phase where you have a Landau pole in the ultraviolet, even for non-Abelian gauge theories, that's why it's called the non-Abelian QED phase. There, you can get an interacting UV fixed point induced by coupling, by the coupling to asymptotically safe quantum gravity. And so this opens up the possibility of a universality class with higher predictivity, where the Planckian value of the non-Abelian gauge coupling is fixed to a fixed point value. So this is kind of the scenario that we have that one could have in mind, where instead of hitting in the non-Abelian gauge sector, so in the non-Abelian QED sector, so to speak, instead of hitting the Landau pole, you have these safe trajectories that are bounded, and then you have the maximally predictive trajectory where the Planck scale value is uniquely predicted. And now one could again ask, if we have such a hypothetical ultraviolet safe completion of non-Abelian QED, would this be compatible with the lightness of fermions? Never mind that we would run into very different phenomenological problems if we were to attempt to replace actual QCD with non-Abelian QED. But just hypothetically, and I'll maybe remark on why this might be useful later. And the answer is yes and no. So there is a certain range of delta n's, so difference between the number of flavors and number of colors rescaled properly, so that 0 equals loss of asymptotic freedom. And the fixed point value of the QCD, or the non-Abelian gauge coupling, diverges exactly at the point where asymptotic freedom is lost, or at least UV safety is lost, because you can, if we leave aside the Banks-Sachs scenario or the infrared conformal scenario out of the equation for the moment. So so in that case, you get this very large G star, this very large fixed point value, and then already within the fixed point regime, you get chiral symmetry breaking. And so you do need a certain, so if you want to have too many flavors, too many fermion components, then you have to overshoot by a large enough margin. And it's kind of interesting whether then, if one could actually do a calculation within enough, with a certain level of sophistication, so that one can also see the lithium-sanino type UV safe scenarios. So basically, large enough asymptotic safety within the gauge, within the non-Abelian gauge sector, whether there would be an interesting interplay between those scenarios and coupling to asymptotically safe quantum gravity. And so what exactly is the window for non-Abelian QED completed by asymptotically safe quantum gravity? Okay, and with that already, I'm kind of nearing the end of my of this talk. So what we found, to briefly summarize, if the color degree of freedom is a global degree of freedom, is a global charge, then an infrared stable fixed point in the space of four-Fermi couplings always exists, i.e. chiral symmetry breaking in the trans-Planckian regime is always avoided. However, the full symmetry of the kinetic term emerges in the infrared only if the Newton coupling is small enough. If color is a local or a gauge degree of freedom, then you do not have an infrared stable fixed point if any of the Newton coupling, the Abelian gauge coupling, or the non-Abelian gauge coupling becomes too large. So this can be understood as that metric and gauge fluctuations enhance each other's chiral symmetry breaking tendencies. And this strengthens the bound on the Planck scale strong gauge coupling. And as an outlook, kind of it would be interesting to see whether one can, or how safely one can exclude tensions with the physically measured value of or the phenomenologically relevant value of the QCD scale. And this would, of course, need a computation within the full standard model, but also it would require one to get a better handle on the systematic errors, which is a whole new can of worms that I do not want to or cannot open within this talk, but it is, of course, definitely something that needs to be looked at in the future. And finally, we also kind of explored to some extent how one could UV complete non-Abelian QED within, by coupling it to asymptotically safe quantum gravity. And this is, of course, not relevant per se within the standard model, simply because our QCD sector is what it is, and it is asymptotically free. However, for BSM scenarios, which one would rule out just based on the fact that they're not UV complete, coupling to asymptotically safe quantum gravity might resuscitate those scenarios that have been ruled out, or that one might rule out otherwise. And with that, I'd like to close. So thank you for listening, and I'm open for questions.
All right, that's all. Thanks, Shouryya, for the nice talk.